Ladies and gentlemen, so we've come to the next chapter, which is all about exponentials. So we need to understand and remember all of our rules of exponents that we've learned before. So here we go. For starters, how do exponents really work? Well, exponents and exponential expressions, it's all about notation, and it's just trying to come up with an easier way to refer to repeated multiplication. So for example, if I have something like 2 to the 4th, where 2 I call my base and 4 is my exponent, I would say something to the power of 4 when we speak it out. If it were 2, we would say squared. If it were 3, we would say cubed. Once we get beyond there, it's the nth power, so the 4th power, the 5th power, the 12th power. So really that's just 2 times 2 times 2 times 2. That's what the notation says. It's 4 times because it was to the 4th power. That's kind of too easy. We need to worry about the actual properties of exponents, which, big long explanation for what it is. Rules we follow which are really observed patterns in the behavior of exponential expressions, which create shortcuts, so to speak. Kind of a mouthful, right? So let's simplify this a little bit. They're shortcuts. Bottom line, that's the way it works. Now, there's a bunch of different scenarios where these shortcuts apply. We've got zeros, we've got negative exponents, products, power to a power, product to a power, quotient, and quotient to a power. In what follows, we'll go through each one of these in a little more detail so that we remember what was actually happening. We'll start with our zero exponents. Now, zero exponents are anything, it says a to the 0 power is equal to 1. That's, the mathy notation for it. Well, in reality, we're saying that anything to the 0th power is going to be equal to 1. Questions you might have, something like, well, why 1? Okay, well, for example, when we take all the factors of some value, and it's prime factorization, break it down as small as it possibly can be. 1 is that basic building block that exists everywhere. 3, 1 times 3. 6 is 1 times 3 times 2. 9 is 1 times 3 times 3. So in reality, if I had something like 2 to the 0 power, well, the answer to that, the actual evaluation of that, is some number. So if it's some number, it's 1 times, and then that exponent says, times 0 2's. So it's 1 times 0 2's, well, all I'm left with is the 1, so 2 to the 0 is just 1. Moving on to our negative exponent property. A to the negative n is equal to 1 over a to the n. 1 over a to the negative n is equal to a to the n. I like to think of this one as the negative identifying that a term is misplaced. Misplaced being it's either in the numerator and should be in the denominator and should be in the numerator, which is what moves a to the negative n to the bottom of a fraction, or what moves a to the negative n out of the bottom of a fraction to being just a regular whole number. Now, I said the exponents were all about repeated multiplication. Well, we got to remember that multiplication and division, they're related. When you divide something, you're really just multiplying by its reciprocal. We remember what a reciprocal is. It's when we invert the fraction, so the numerator becomes denominator, denominator becomes numerator. So if I say 3 divided by 2, that's really 3 times 1/2 because I multiply by the reciprocal of 2, which gives me 3 over 2. Couple of examples for us. 3 to the negative 3rd, 3 to the negative 3 power. Well, if we follow the rule that we just had, that means that I should rewrite it as 1 over 3 to the 3rd power. That's 3 times 3 times 3, which is 1/3 times 1/3 times 1/3, which is 1 over 27. All of those representations are equivalent. If I have 2 to the negative 5th power, well, I could rewrite it as 1 over 2 to the 5th. I could write the repeated multiplication. I can understand that that's really just 5 fractions, all 1/2 being multiplied. It's 1 over 32 when it's evaluated. And an example of the other form, where what if the negative exponent's already in the denominator? Well, I can either recognize it as 4 to the 3rd, or I can go through that whole process. 4 to the negative 3rd is really 1 over 4 to the 3rd. Well, if I divide by a fraction, I multiply by its reciprocal, which is how we get to 1 times 4 cubed over 1, or just 4 cubed. 4 cubed, 4 times 4 times 4, we get 64, regardless of which way we think about it. Moving on. Our product property. that says that a to the m times a to the n is equal to a to the m plus n. In reality, it says anytime you multiply two exponential expressions and they have the same base, recognize that a is the same in both of those expressions, we add the exponents, keep the base the same. So let's go back to repeated multiplication to make this clear, right? This is a shortcut. We need to remember this is a shortcut for not always having to recognize things as repeated multiplication. So 2 cubed times 2 squared. We could expand it out. Sum total, we've got 5, which 5 happens to be 3 plus 2. Our power to a power property. A to the m to the n is equal to a to the m times n. So if I have an exponential expression and I raise that to another power, in this case to the nth power, it's the equivalent of keeping my base and multiplying my exponents. So we'll use repeated multiplication to get this done again. That's going to be a common theme. I'm going to stop actually writing that in. So 2 cubed squared. I can rewrite that as 2 cubed times 2 cubed, taking into account the purple exponent. Inside of each of those parentheses, I can expand it out with repeated multiplication. I've got 6 total, so all said and done, that's 2 to the 6th power. 6 happens to be 3 times 2. This is where we decide that that's a shortcut, and we're going to go with it. Our product to a power. That means I'm raising things being multiplied to some power. In this case, a times b to the m is equal to a to the m times b to the m. So anytime you have a product raised to a power, we take each factor in that product and we raise it individually to the power that we see. Back to repeated multiplication. 2x to the 3rd power. Well, if I take the 3 into account, that's really 2x times 2x times 2x. Rearrange things a little bit because we have those properties that say that multiplication allows for rearrangement as long as everything's only accounted for once. So I'll rearrange all the 2's together, all the x's together. That gives me 3 2's total, 3 x's total, so I can rewrite it as 2 cubed times x cubed, which, if we go back to where we started, that was each factor, 2 and x, being applied that 3 of an exponent. Our quotient property. Everybody loves fractions. Well, fractions work the same way. If I have a to the m over a to the n, there's a shortcut. I don't have to expand it all out. I can just rewrite it with the same base and subtract my exponents. Here we go on the explanation. If I have, for example, 2 to the 5th over 2 squared, I can rewrite that as 5 2's over 2 2's. Understanding how we simplify fractions, 2 of those 2's are going to cancel, leaving us with 3, which is 2 cubed. Coincidentally, 5 minus 2. Our power of a quotient property. A over b to the m, right? Quotient. It's the results of division, which means it's going to be a fraction when we represent it. So a over b to the m power could be rewritten as a to the m over b to the m. Each part of the quotient, we call them the dividend and the divisor, gets applied that exponent, similar to the product to a power. So 2/3 to the 3rd power means 2/3 times 2/3 times 2/3. That's just applying the exponent. I reorganize things a little bit so that I can actually see what's going on. I end up with 3 2's and 3 3's, which is all said and done is 2 cubed over 3 cubed. That's all of our properties that we apply to exponents. Now they can be applied in combination. Sequence doesn't ultimately matter. What matters is that we appropriately apply them to the right situations. We'll take a look at a bunch of examples in class tomorrow.